Yeah, the recording should be started. Okay, so let us start basically today's topic. So we were basically discussing detection or sort of classification plus localization. But mostly the idea was to regress the bounding boxes. So we were just sending images or crop of images through the deep nets, and the ultimate basically output would be 4 or k times 4 coordinates, and the classification level. So there were two heads: regression and classification. But mostly the localization part, that is the bounding box, they were getting basically we were getting it from regression. So we have seen this. Now detection as regression, that's what we were basically discussing, as I said. Okay, sorry. Now in detection, you don't know the number of objects present basically in the detection problem. So in the detection problem, in an image, you don't know how many objects can be there or how many instances of the objects can be there. But for the regression problem to work, or the regression way to detect, should I mean assumes that you know the number of objects present, 1, 2, 3, 4, whatever. So it is problematic to address detection as regression in the most general setting. So how many output neurons to put if you don't know the number of objects? So that is the problem, right? So how do we tackle this? And for that, as we earlier said, that regression and classification are your two most loyal friends in machine learning. So you basically, if you are not getting something by regression, you try with classification, trying to basically pose it as a classification problem. And how do you do it? So for detection, apply a CNN to many different crops of the image. CNN classifies each crop as object or background. So these crops are sort of giving you the localization, that okay, I mean this is the crop. It might contain or might not contain some object, and who will tell that whether it contains or does not contain is the CNN. So we have seen the use of or some sort of an initial use of or preliminary use of crops in the overfit architecture, right? So that's how we intuitively explain. But later overfit actually sent not just crops but the full not crops but the full image by using that 5x5 conv at the last conv layer, right? So that we discussed yesterday. So but at least we have we got some familiarity that okay, crops can also be passed, and the network can be asked that whether this crop belongs to some object or background. So this is the idea, that okay, this is the image. Let's say the first crop is this, that okay, this sort of this part of the image, that is this blue bounding box, this part of the image, you want to test whether it's an object or not. You pass it through the CNN classifier. It may be pre-trained. You may train it with training data from detection data set or classification data set, and then you pass it, and it says that whether it is dog or cat or background. Actually, it is a background, so it says that okay, we expect that it is a background. That is the network tells it as a background. Now next crop may be this, it's a dog, so the network tells it as a dog. Similarly, the next one is again a dog, it tells it as a dog. Next one is a cat, so it says that it's a cat. Okay, so this is a very naive or simple way to do detection as classification. So you just try to find out crops, and then just pass it through the classifier, right? So that's as classification part comes. That's why. But this is the problem here. So you need to apply CNN to a huge number of location scales and aspect ratios, very computationally expensive, because you never know where the objects are. So you have to try them all, right? So try all possible crops. And that might, or that will actually mean it's computationally expensive, because you have seen in say some other conv architectures when we discussed about it, say the VGG architectures. I mean, at least for VGG, we have done this computation analysis that, okay, how much computation is there in the early layers, how much on the later layers, and so on. But it's a lot of computation in millions, right? So if you have to pass all these crops for one single image through these CNNs, and you need to wait for the result, I mean, your autonomous driving dream will be far away, right? I mean, it will not be a real-time detection. It will, maybe it will wait for a minute or two for each frame of say a video feed is coming, say, from the dashboard camera, and each frame it will take say 1 or 2 minutes. So that's not practical. So how do you basically get rid of it, right? So yeah, so this is the way that we will start to learn how to get rid of it. So we will, I mean, we are now discussing detection as classification, and we have seen its advantage and disadvantage. Okay, so advantage is that, okay, you don't need to know how many objects are there. You can just try some crops, but these some crops can mean that exhaustive number of crops. So that is the disadvantage. So this was the disadvantage. Now, if the classifier is fast enough, this can be actually done. So if you have the classifier which runs very fast, not CNN. CNN is not fast. So in that case, you can do it. I mean, close to real time maybe. Okay, that was actually the sort of idea that prevailed before pre-deep learning era. So or before deep learning sort of got its resurgence, basically pre 2013, 2012, around that time. So what are those sort of classifiers? SVM, a linear SVM can be one, a random forest, etc. So linear SVMs just operates on linear basically operations. So it is fast. So deep learning classifiers, on the other hand, first this is one way to basically get rid of it. So do detection as classification and do it fast. This is one way. What is another way, which is using deep classifiers? You actually don't try them all. So what will you try? You will try only those which has lots of, I would say, possibilities, or lots of chances of containing object. Only those crops, not much of the backgrounds. So first get a teeny subset of possible positions which can contain objects. Only these are passed through the deep classifiers. Okay, these are some of the crops that I think may contain object, may or may not, but there is high probability. So then we will try to refine, sort of using this the deep learning classifiers. I have touched on this idea yesterday after somebody asked one question. So that is sort of the idea that we will discuss today. So the possible positions, these teeny subset, are called candidate proposals or region proposals, or sometimes it is called region of interest, because these are the candidates for containing objects. Only these candidates will be evaluated by the classifier. So these are candidates, they will be evaluated. Sort of you are shortlisting some candidates in your interview, and then they will be evaluated, they will be interviewed, right? So something like that. So that's why it is called candidate proposals or region proposals, because these are the regions that you will pass through, the regions of the image that you will pass through the classifier to get to know whether this contains an object or not. And or another term that is also used is region of interest. Okay, now this is the pipeline basically. So this is how it generally happens. So it is the original image, then these proposals or region of interest or candidate proposal that is generated, and these are the region proposals. So What are the region proposals? So that I said that has a high chance of containing objects, and generally they are done using taking advantage of low level queues. I mean, it does not involve deep learning or deep classifiers, which are computationally expensive. So these generally are unsupervised approaches. These generally are not learning based, but we will see a learning based one at the end of this RCNN architecture discussion, which will not be today, but next Wednesday. Okay, but I mean, yeah, so the initially what people tried to do is getting these region proposals using low level queues. What are low level queues in an image? So edges, connected components. So the idea is that these regions, these proposals, they are sort of very similar in properties. Some of the properties, maybe the color. I mean, that's what we see, that color, if it belongs to a single object, mostly the color will be very similar. If it's a cat, then yeah, I mean, it may be one color, one single color cat, or some of the regions may have different colors, but may not be more than 2-3 colors. And it's not haphazard, it's not random. Even if it is 2 colors, there are contiguous spaces of say colors of these different colors. And even if there are like these sort of not exactly same color in contiguous neighboring regions, then the other low level cues can help, say texture. So the texture is very similar, very uniform. So this proposal mechanism can take advantage of low level cues. So on a high level, these are some blobby sort of areas, regions in the image that has very similar properties, and those properties can be edges, connected components, textures, colors, other things like shading, etc., many other things. And those you can actually compute without relying on a machine learning technique, and that are generally fast. Okay, so that's how you get the region proposals. Now, if you get the region proposals, then only you evaluate on this, not on exhaustive sets. And then say, okay, when you pass this crop, it is saying that it's a cat. When you pass this crop, it is saying that, okay, this is not a cat or dog. Say your detector is just detecting cat or dog. So this is not a cat or dog. So everything else is background. So this is a background, this is a background. This is not a full dog. So this is sort of background. Or not dog. Background basically means not your object of interest. Okay. So classifier can be now slower but more powerful, because generally the faster classifiers are linear classifiers, or it may not be powerful, but you want to use a powerful classifier. So for that, what you are saying is that you are sort of dividing it into 2 steps. One is generating candidates, another is using powerful classifier. So these generating candidates, it has to be then fast. Okay, and it has to be very precise, that okay, you don't give lots and lots of candidate proposals which may not contain an object. Okay, so this is basically the pipeline. I will go into 2 pre-deep learning proposal generation mechanisms, but on a very high level, because one of them is used extensively in 2 versions of RCNN. But again, it is too high level. Very briefly, I will go into it. One method is just, I think, 2 slides. Another method is just 1 slide. But I would encourage you to basically read these papers. They are very good. I mean, low level vision, how does it work? You can have much better idea. Anyway, so one of them is the selective search algorithm. So this is a paper in IJCV in 2013, as he said here, from Theo Gibbs and others, selective search for object recognition. So what does it do? It gets an input image, then it tries to find iteratively these crops that are given here. Okay, and it tries to actually rank them. So you see that there are lots and lots of crops, but it tries to say rank using some score, and then finally the classifier will, I mean, these are candidate proposals. Okay, so the classifier will take, say, top 2000 or only top 1000. Only those will be passed through the classifier. So how can you get what are the top ones, right? So for that you need to have some rank or score, right? So that will come. Now it does it iteratively. What does this iteration mean, or what does it do in each iteration? So at the very beginning, it uses very one low level segmentation algorithm. So if you have taken any computer vision course or machine learning, unsupervised machine learning ideas, if you have, then you know there are many segmentation methods. For example, say watershed segmentation or graph-based clustering. So segmentation and clustering, they can be thought of very similar problem, because in segmentation you also want to cluster some images which are of similar properties, right? Again, properties I am probably using in double quotes. So properties is basically the color, texture, edges, characteristics, etc. Okay. Now, you use one very low level segmentation algorithm. Here it was used, I think, graph-based clustering, which was 2008 or 9 paper by Pedro Felsenswab. So Pedro is one of the eminent researchers in detection community. So before deep learning, the most popular detection paper was DPM, deformable parts model. So that was from Pedro Felsenswab. So that's also a very good paper. I mean, if you are interested, please look into it. I mean, it has very good physics analogy. If you like physics, it will sort of the spring mass system. You will like that. Anyway, so from another paper of Pedro, that that is graph-based clustering, you actually cluster, you get these segments. And what are these segments or clusters? And one more thing is, it is deliberatively over segmented. That is, if some region is segmented, say this, it is basically the segmentation algorithm makes sure that this segment does not span more than one object. So this segment does not have parts of two objects, so to say, or the whole of two objects. It may not contain the whole of one single object, but it is it is made sure that it does not go beyond one object. Okay, so that's the over segmentation means. So then the idea is that in the next iteration, it will try to look for neighboring regions to merge, so that again it does not go beyond, say, the one single object. Or rather, so to say, that from over segmentation we are trying to go to under segmentation. That is, at the end, the whole combined region will be the whole image. Okay, so basically two neighboring regions, they try to merge, so that the idea is that it belongs to one object. Okay, but of course, in a single image there might be many objects. So when do you stop? It says that you stop when the whole image becomes one segment. Okay, then how is your objective served? That okay, if I get this whole image as a single region, then should I pass this to the classifier? No, that is not the idea. That is where this ranking idea comes, because after each iteration you get these segmented regions and you rank them. So you get a combination of these segmented regions, a union of the segmented regions. So all the segmented regions here, all the segmented regions here, all the segmented regions here, they are sort of combined. That is, union of these are taken, and for all of these you score, and then from there you take the top 2000. That this bigger one may come, but it depends on the philosophy of finding the similarity score. So again, it's a pretty high level description I'm trying to give. Even just for the similarity computation, they have 80 different methods, they are saying in that paper. So and these are mostly, as I said, this term low level I'm using, that means it's influence or sort of motivated by sometimes how humans do it. So but exactly it may not be how humans do it inside the brain, but at least some human form is there. Now, okay, so you get these highly over segmented regions, then you take the very neighboring regions. Of course, there is no point merging, say, a region here and a region here. I mean, there is very less chance that they belong to the same object. So this is, say, after, say, n such iterations, you get this one. So maybe that, okay, for this area, say, whatever, I mean, this may be the face and so on. So this is that area. And then finally, not finally, I mean, this is another, say, n plus mth iteration, you get this. And then finally, at the end, you will get the whole image as one single region. And for each of these regions, you extract the tight bounding box, say this. And that is your candidate proposal. Okay. And then, as I said, which I'm not going into detail, the similarity score generation. For that, I think I'm referring you to the paper. Now, this is the algorithm in the algorithmic form. It's a very simple algorithm, but yeah, I mean, the details are, I would say that, I mean, that depends on these handcrafted features, and that's where people were a little uncomfortable dealing with these handcrafted features. Okay, some research groups, some students have found that this works well, maybe age, maybe trying to orient them, the ages in say 8 beans, not say 10 beans, according to angle, then take histogram, not taking histogram. So these are handcrafted features, right? So these handcrafting is sometimes frustrating. I mean, okay, you try something, you don't have so much explanation, but that's where I think the deep learning literature came into prominence, that okay, you don't need to handcraft, the architecture will learn the feature by itself. But anyway, I mean, they are fast. The first, I mean, if it works, then it is fast. So something like that. Anyway, so I think I am going a little aside, but let's come back to this this grouping algorithm. So you have input image, you will ultimately want to have set of object location hypothesis. Sometimes they are called hypotheses. They're basically the same thing, the candidate proposal, etc. Now, first obtain initial regions using 13. So 13 is that graph-based clustering method paper. You get this highly over segmented regions, this R1, R2, Rn. So these are basically, these regions. Okay. Now, initialize a similarity set, which is initially null. So how do we basically fill up this set? We will come. So similarity set is basically, it will contain the similarity between all the neighboring pairs. So for all neighboring region pairs Ri, Rj in this R, in the initial segmented, over segmented image, you calculate the similarity, and then you basically store them in this set. Right now, after you are done with this, while S is not null, so we have filled up this S, and then it will again become null. How it will become null will come, but until it is not null, you do this thing. What? You compute the or you get the regions, neighboring regions, or the pair, neighboring region pair, which has the highest similarity. So what are you filling in this S? The similarity between neighboring region pairs, right? So you get the highest one, the highest neighboring pair, then merge. So it's a very simple idea that, okay, you get similarity scores here between region pairs, neighboring region pairs, and you merge the highest. Then if you are merging, say, this and this, then what do you need to do? From that similarity set, you need to delete the similarity between this pair and this pair, this pair and this pair, the same pair, I mean the same, sorry, not pair, this region and this region, this region and this region, the same region and this region, this region and this region. Basically, you take one constituent of the merged pair, and every neighbor of this constituent, you delete the corresponding similarity with that neighboring pair, basically. So because you have merged, so this area has become now 1. So with, I mean, the similarity pair between this and its neighbors and this and its neighbors, that you need to delete from that set S, but at the same time you need to add similarities between this big region and its the big region's corresponding neighbors. So that is what is done in the next 2 lines. So you merge, then remove the similarity of Ri is neighbors and Rj's neighbors, because that are the 2 regions that you have merged, and then calculate the similarity between RT and its neighbors. RT is the merged basically region. So S, then your new similarity set is of course the union of the old one, that is after removing of course, and the new ST and this new R, that is from R you are not removing RI. You remember that, because that's the union of all the regions in all the iterations that you are taking. Okay, so have a look at this at your leisure time. I think I have tried to discuss as much as I can. Then basically after this S is 5, that is there is one single region which is the whole image. You extract object location boxes L from all regions in R. So all regions in R means this R is the union of all the regions. So you basically find the tight bounding boxes from there, and then you compute the basically rank and so on. So those things I'm not going into the detail, but this is the basic idea. Okay. I'll quickly go through these last 2 slides and then I'll stop for questions. But if you have any questions, you can always raise your hand. So this is another approach that came in 2014 ECCV. Sorry, here. This is from Larry Zitnik and Piotr Dollar. And then, okay, sorry, not then. So these edge boxes actually uses the idea that edges are very good cues for finding objects. So edge boxes depend on fast scoring evaluating method for bounding boxes. And first edges are extracted for the whole image and they are grouped according to their similarity. Again, this similarity calculation, etc., I'm not going into. The main idea of scoring boxes builds on the fact that edges tend to correspond to object boundaries, and bounding boxes that tightly enclose a set of edges are likely to contain an object. So edges tend to correspond to bounding boxes or object boundaries. I mean, that is clearly seen. I mean, this wheel, the edge, if it is a closed contour of edge, it is very likely that it belongs to an object, or it's an object. So you try to evaluate some bounding boxes, and if you find that there are closed contours of edges, then you just say that, okay, this is my one of my candidate proposal. If it hangs, suppose you have something like this, then this edge, whatever is there, it hangs. It's not a closed contour. Or if you have some bigger box which has a lot of closed contours, then it might be that there are lots of objects in there. So this is sort of the idea. Again, I am not going into the detail. It's very much not I mean, beyond the scope of this course, but I encourage you to basically go through these papers. I mean, these are very, I would say, different flavored papers that we have discussed till now or will be discussing. So yeah, so one of the advantage is that it is 40 times faster than selective search for with basically greater recall. That is more recall. You by now you know what is precision and recall. So 75% recall means for an image, 75% of the objects are retrieved with 40 times faster speed. So again, this I know I have gone through very briskly, but yeah, we will go into more interesting stuffs very soon. And this is just one component of it. But the one take-home message from this is that you have methods using, or fast methods using low-level computer vision cues to get class agnostic regions. So basically, these are object regions, but it does not say which object it is, whether it's a cycle or cat or dog, etc. It does not take, but you have some methods which are fast and which can give you some good candidate proposals, which you can then pass through a better classifier, right? This is one table taken from another paper, which actually tries to evaluate a few of these region proposal generation methods. And I mean, the more number of stars or ticks are the better, and of course the low number of time. So edge boxes tend to be, I mean, in that paper better and so on. But selective search is also not bad. And we'll see that the RCNN ideas that we will discuss next, it uses mostly the selective search. Anyway, so this concludes this first part of the detection idea. I mean, I will go into more of detection architectures, which is detection by classification. If you have any questions, please ask. I think there is one raised hand I'm seeing. Yeah, Shreyas, yeah, if you can ask.
Sir, yes, sir. So grouping these regions, it can be done till the entire image becomes one region, right? So like, are we deciding this based on number of objects? Like if we know beforehand there are 7 objects, we go till 7 regions. Is it like that?
No. It's like a, I mean, you always go till the whole image is taken as a region, but that might mean that for different image, you will have different number of basically candidate proposals, because here it might be just for some ballpark number, say this is 500 proposals. Here after say n iterations you mark, it is suppose say 200, and suppose this is 100, and then so on. So you are actually getting these many regions, okay, these many regions. So for each iteration you are basically bounding this or getting this tight bounding boxes. So if you are, I mean, just if you think about the ith iteration and i+1th iteration, then only a few bounding boxes you are changing, okay. So only few gets deleted. Deleted means deleted from the image, but remember it is not deleted from the set of locations. See this R. So R is the initial number of regions, right? Then you are getting this RT. You are not deleting RI, RJ. You are just adding RT. Okay. So you are getting always this sort of increasing function, right?
Oh, yes, sir.
Right. So that's why you can get a lot of this search. I mean, what I'm telling as regions, if you just take a tight bounding box, that's the locations. So this is the region, but this is the tight bounding box. Okay. So corresponding tight bounding box is maybe here. Okay. Okay. So now if you have so many regions, how can you, I mean, you don't want to basically evaluate the so many regions. Just one extreme example is that the last region, this is this whole image. If you are evaluating, passing it through the whole classifier, you are not doing anything good. You are just doing image classification, right? So to basically help in that respect, you are sort of sorting. Suppose this sum is something like 4,800, whatever. You are sorting all these 4,800 boxes according to some score, and you are taking this top, say 2,000 boxes. Only those you will evaluate. Okay. Then these top 2,000, what does the score signify? The score signify that it has higher chance, or higher the score, that means it has higher chance of basically enclosing an object. So you are only evaluating by your classifier later the ones that are most probable. So you are not evaluating all of these by the classifier. You are just taking say some top. And if you see, I have not discussed it much, this recall, the 75% recall with 800 box. What does it mean? For edge boxes, if you take top 800 boxes, then say you have say 5,000 images. For each of them, you take top 800 boxes. Okay, so 5,000 times 800, and you have in each of these 5,000 images a total of say 8,000 objects, total instances, right, in those 5,000 images. So 75% of this 8,000 is how much? 6,000. So if you are evaluating or basically taking this 5,000 times 800, these many regions, you are sure to get 6,000 of the true objects out of this 8,000. So that is like the 75% recall. So you remember recall is, I think it is in this, in these slides. So definition of recall here, right? Recall is how many relevant items are selected. So relevant items are 8,000 in total out of these 5,000 images, and 6,000 you have obtained via those 800 top regions in all these 5,000 images. So is it a little clear? I mean, does it answer your question?
Yes, sir. Yes, sir. Yes.
Okay. Thanks. Any other questions from anybody? Okay, if not, then just give me like 2-3 seconds. I will have to switch to the other PDF, like other slide. I could not actually fit it in this slide because these links, these top links will then, I mean, I'm not being able to fit it in the slide. So let me just, actually I need to switch to my computer then. So give me some seconds. Let me share. Okay. I hope you can see my screen. I'm just allowing you to unmute anybody.
Yes, sir.
Okay, great. Okay, now let me go to this one, basically. I think it is fine. Okay, well, let me just do this annotation tool. Yeah. Okay, so again, detection segmentation. This is the part 2 where we will discuss about, again, I mean, I have kept the agenda same. It is just the part 2 of the detection basically discussion. Okay, so now that you have you are equipped with the arsenal required to understand this RCNN or the one of the basically phenomenal I would say philosophy in detection, and that actually came just after AlexNet and VGG. They became so much popular and did wonders in classification. So let us basically go ahead without further ado, because we know now about the components. So how can we basically club these components to get a very good detection system? And that is what is done by this RCNN. So region convolutional neural network, RCNN means. And it actually, you see the term region has started to appear. So this region proposal, candidate proposal, region of interest, this has this term region. So you have the region proposals, and then you use the CNN features for classification. So this is a paper from Berkeley guys, and it appeared in CVPR 2014. And at that time, it caused pretty much star, because I think it almost doubled the performance from the pre-deep learning, basically pre-deep learning detectors. Okay, so what you have is an input image. Now you basically, now that you know what does selective search or edge boxes at least give output or do, you basically run the selective search algorithm. In this paper took the region proposal generation as a selective search algorithm. So it basically gives, after you pass this input image through the selective search algorithm, suppose these are some of the top candidate proposals, these. So regions of interest from a proposal method, around 2000 they took for evaluation. Now you can understand what they will do. They will try to just pass it through a classifier. So for classifier, I mean, since we are in deep learning class, the classifier is You can think that the classifier is a deep learning classifier, but it is not exactly the full deep learning classifier. That will come later, but let's see what it is. First of all, if you want to use a deep learning classifier, say VGG. For our case, let's say the to-go example is VGG. So if I have just opened, kept the VGG slide open for your easy reference, you see the input has to be 224 by 224 by 3. 3 is this, that's the color channels, but the height width has to be 224 by 224. Otherwise, it will not work, because there is this resize and so on. I mean, it will not give, it will not get the requisite number of input in this fully connected layer. Okay, now, okay, sorry, not this one, this one. So you warp the image region. So these are the regions, but they may not be 224 by 224. Even if this is, this input image is more than 224 by 224, it's a high resolution image, say 500 by 500. Not that all the image regions will be 224 by 224. So the first thing is that you do is basically you warp it. That is resize it to 224 by 224. Not that all the regions will even be square even. Okay. Now you see what you do is you pass it through the coordinate. So you take the basically say against the same VGG net. So you give this, now VGG can take this to 24 by 224 by 3, and then you pass it, say, till this layer, that is the last conv layer, which gives the 7 cross 7 cross 512 this feature map size, and you resize. So I have discussed about resizing even yesterday. What do you mean by resizing? So you get these numbers, and for each image or each warped region, you get these numbers. Now what you do? You basically pass it through a SVM classifier, because that's what our philosophy was earlier, right? That we told that we get some candidate proposals and then we classify. So for classification from the candidate proposals, you are generating features which has dimension 7 cross 7 cross 512, which you can put into a long vector, and that then you pass through a SVM classifier. Now it might come as a surprise, why SVM and so on. So the easy answer is that these guys were actually taking part in a challenge, and they had their own pipeline for earlier years also. And at that time, before deep learning, SVM classifier was very popular. SVM was very fast also, the linear SVM. I think there was a popular library called libSVM. You might know about it. So because they were using it earlier, they just thought that, okay, if they want to change everything at the same time, it might not give them edge in the challenge. So it requires a lot of tuning and hyperparameter setup and so on. So they just tried to change this handcrafted feature extraction, which was here. So previously also these ideas were there, that you generate these region proposals, but then these handcrafted features were extracted. For example, those hog histogram of oriented gradients, then shift scale invariant feature transform. There were others also, had a leaks feature, many other handcrafted features. And those handcrafted features were passed through SVMs to classify. Here, what they changed is that they basically took a pre-trained coordinate, pre-trained VGG. You can also fine-tune that up VGG or a coordinate that is pre-trained on ImageNet. You can fine-tune all on these detection images. You just take crop, ground truth crop of this human. You take the ground truth crop of this horse, and then just say that, okay, there are two examples, training examples. One is of human, one is of horse, and you pass it through this coordinate and fine tune. You have to fine tune, otherwise ImageNet has 1,000 classes, and these guys have done it on Pascal dataset. I think Pascal has 20 classes, so those two don't match, and so the classifier will then output only ImageNet classes, which will be definitely wrong. So again, what we discussed till now is that you take the input image, you pass a region proposal method, say pass the image through a region proposal method, say selective search. You get these region proposals. you warp them to so that it can so that a VGG net or a corn net can take these warped images as input and give the features, output the features, and these features you pass through SVM classifier. Then this SVM classifier classifies it to 20 classes of Pascal. One additional thing these guys added is this bounding box regression. So what is the idea of this? So you may think that, okay, why are we then going back to regression? And we said that we are trying to do it by classification, the detection by classification, and that till this slide it was like that. You are classifying the regions. The thing is that they saw that if they use again add one bounding box regression, it can basically correct some of the mistakes. What are the corrections? That, okay, these region proposals, they don't give very precise bounding boxes. I mean, it can be a little off. It may be. So you see that this human is it's not completely basically enclosing this whole human. I mean, this bounding box is not enclosing this whole human. So if you use a bounding box regressor here, where you have say the ground truth, during training, where you have the ground truth bounding box for this whole human, you say that, okay, this is my predicted one and the ground truth one is this. So try to regress these things, slightly shift these corners to those ground truth bounding boxes. So it generally pays off well. So this bounding box regression is also added as another component. So this is what they have added new also, this bounding box regression. So this is the whole pipeline, but it's a very complicated one. See, the parameters are like threefold. One is ConNet. You have to fine tune, as I said. You can take a pre-trained classifier ConNet or pre-trained feature extractor. That is just the con part of the VGG set. Which is pre-trained on ImageNet, but of course the ImageNet classes and these Pascal classes, they don't match. So you need to also basically try to sort of make this feature extractor compatible with the features coming from these classes. Maybe that horse was not there in ImageNet. So, but you need to equip this ConNet with horse-like features, okay, so that it is capable of extracting good horse features, which will help these SVMs to classify. Then the SVM classifier you need to train with these features. You need to store maybe these features from these warped images. Then you need to invoke the SVM training and also the bounding box regressor. The bounding box regressor also have some fully connected layers, and that also has some learnable parameters which needs to be trained. So this is a little convoluted way. So you pass this image through this region proposal network. You warp the region proposals, then you generate the features, you store them in a hard disk. Then with these features you train this SVM and bounding box regression, and not to forget, you need to also train this ConNet with this detection images, right? So I remember, I think in 2014 when this code came out, it was in Cafe at that time. No PyTorch, TensorFlow was there, so in Cafe, I mean, in the README of that code, it was said that you should have at least 200 GB of hard disk space. But you know that, I mean, in Pascal has like 13,000 or 15,000 images, or 20,000 if I remember it right. You don't need to have 200 GB of space to store these many images, but you are storing these features, right? All these 2,000 proposals, features, which are floating point numbers, long vectors, 4096 number or whatever. So you need space. So that's a very convoluted way. Let us come to the results, and then I'll come to the what you train there. So the result is very encouraging, big improvement over the pre-CNN model. So this is the blue ones are Pascal VOC 2007 partition of the dataset, and this is Pascal VOC 2010. So they added some more or refined some of the images and so on in 2010. but let's say this Pascal VOC 2007. So DPM is that Pedro's work, that deformable parts model. It gave 33.7 in 2011, right? Then something which is also pre-deep learning, it's region-lets. That is, it does not use deep learning approaches. It increased it to 41.7. Now RCNN gave a shoot of this much, that is 54.2, using AlexNet feature. Now if they use bounding box regression, they it gives even more, I think 4% more improvement. And then if you give it a better feature representation, that is BGG16 instead of AlexNet, it gave even more, 66. So from in 1 year almost it is from 41 to 66, and in 2 years it's doubled, like so DPM2, which is huge. So that actually caused a lot of stir in the community around that time. Now this is the again, but the disadvantage sort of, I mean, it's not disadvantage. I like this evolution of RCNN architectures. You will see that, okay, these are some of the limiting traits which they actually got rid of in their next architecture. So one is this fine-tune the network with softmax classifier, that is this ConNet, the fine-tuning part that I told. Train post-hoc linear SVM. So post-hoc means you extract the features of these region proposals and then you basically train these SVMs, and also the post-hoc bounding box regression. So this is the ad hoc training objectives. Training is slow. It is 84 hours, takes a lot of disk space, as I said. Inference is slow. It takes almost 47 seconds, almost a minute with VGG16, which is like, I mean, far from real time. Fixed by something called SPPNet in 14, but we will not go into this paper. Rather, we will discuss about the evolution of basically the RCNN architecture. So I think I will stop after this slide. So this is sort of the basically takeaway message for the RCNN, take-home message for RCNN architecture. I will come back to these images every time I will introduce other RCNN architectures. So what does it say is that there are three important components of a detection pipeline. So region proposals, that is which crops you will evaluate, or which crops you will classify. So I will use interchangeably evaluate or classify. Evaluate means just, again, that analogy that I gave, that interviewing and so on, right? So basically it is just trying to classify the region proposals. Then this feature extraction from these region proposals, and then the classifier part, which is SVM in case of RCNN. So what happened earlier, pre-2012, is that region proposals were there. The idea of selective search, these edge boxes, they were there. But since the classifier was fast, SVM, linear SVM classifier, people could afford to basically densely evaluate. So dense cropping, they were, it was said. Said they will just crop almost everything. So almost exhaustive search sort of idea. So exhaustively they will take these crops and evaluate using this classifier. But after taking these crops, they will do the feature extraction by a handcrafted. I mean, this is one image of hog feature. So both are very fast. I mean, this dense cropping or this handcrafted feature generation, they are fast, and even the classifier is linear classifier. Everything is fast, but the performance was not good enough. So it had ad hoc sort of combination of three different ideas. So even if you get some good information from this classifier, you cannot sort of pass it through to this feature extractor. Or if the feature extractor is good, then of course it goes to the classifier, but it cannot come back from, say, this to this and this to this. And through back propagation, actually in deep learning architecture, this can happen. Now in RCNN, what do? They changed it to from dense cropping to region proposals, and this feature extraction they changed to con features, not the handcrafted features. The classifier is still the SVM. So region proposal selective search, feature extraction is CNNs, and classifier is linear. So I shall stop here and we will actually take a look into how to basically get rid of these disadvantages, the time, then this end-to-end training idea, that is you are sort of clubbing these three different ideas, and then I mean pipelines, and doing so this getting the good information back from the later part of the pipeline, how to incorporate that using in next week. So tomorrow there will be no class. If there is any question, please ask away. This is a good time to ask. I shall upload the slides today, and I think I have uploaded the recorded video yesterday's recorded video already. Okay, if you don't have any questions, please read these slides. I will upload it and then come prepared in the next class. Thanks a lot. I'm ending this meeting.